Hi everyone, and today I'm privileged to have Marius again to come talk to us about the Symbolic AI framework. So the last we stopped at the Symbolic AI paper, we have reached the evaluation section. So just a recap of the paper, Symbolic AI basically starts off with symbols and then uses symbols to manipulate via expressions. And you can interface with various engines like the OCR, large language models, Wolfram Alpha, and so on. It's a very flexible framework that allows you to interface with multimodal stuff like text, image, video, and so on. So we have covered the majority of the paper. And now let us move on to part 2, which is on evaluations. So I'll pass the time to Marius.
Thank you very much, John. So yeah, thrilled to also talk about the evaluation now. So let me quickly share my screen. So here we go. So you should be seeing the paper, right?
Yeah.
Maybe a bit zooming in. So let me see. Once. Good. Directly scrolling down to the evaluation section. So we had some ground to cover. Yeah. Okay. So yeah, in our paper, mainly what we evaluated now is, we were interested in how can we now create, since we can use different solvers and different, generative processes and so on, whatever model you prefer, let's say GPT-4. We thought about like when creating this kind of like multi-step, generative processes, if you have like, let's say an entire computational graph where you would say each node is, one part of this generative process. We thought about like, how can we evaluate that? Because, you can stitch everything together. You can compose basically this computational graph, but and run it obviously, but at the end of the day, it's obviously interesting. How can you like control it, like measure maybe it, how far you're off to what you would have expected. And that's kind of the whole point of the entire evaluation section of our paper. Yeah, and what we evaluated here is we basically looked at several large language models, so contemporary versions of them. So obviously GPT 4 Turbo, in this case, this revision 11.06 at the time. So here we basically just wanted to look at like what kind of the most proficient model at the time. And maybe if we look a bit at the graphics, that makes it a little bit easier to grasp. So kind of what is the most proficient one? Then we also looked within our computational budget. What we can also work with is obviously, and resources is GPT 3.5, which is usually the model mainly used nowadays. Because
Quick
it's
question here.
fast.
Which
Yes.
is the best model based on your eval? I think that's what most people are.
GPT-4, I would say GPT-4. So that's no surprise, I would say. But we also like looked into like compared to Gemini Pro, because so we selected Gemini Pro because we had no access to Gemini Ultra via API. Also for Gemini Pro, we even had to VPN ourselves because in Austria there you don't actually get access to this model. So basically we even tried we contacted Anthropic to also get access to Cloud 2, but they never replied to us. So, and the registration never went through. So I don't know. But if we get some, further access for the support, then we might, update in the future and put
Yeah,
more
the
other
results are
models.
quite interesting. Like, because when Mistral 7B marketed themselves, they said they were as good or even better than ChatGPT at some well-known benchmarks like MMLU and so on. But there's a huge gap here, right, in between Mistral
Yes.
and GPT 3.5, even ChatGPT. So
Yes.
maybe you'd like to walk me through like
Yeah.
how different is your benchmark compared to existing ones? Yeah, maybe you could just share that because like why is the result so different?
Yes, so exactly. I'll go for that. I just wanted to give you a short overview, like what are we comparing? So this is kind of like the idea was to have the most proficient one model, then the mid-range model, like this usual 7 billion-ish plus whatever range of models compared to each other, because for that we had like also hardware resources and budgets, and then like the most like what is randomness, if you would just look at that. And there are like these 5 different categories that we looked at specifically. So we looked at these, what we called associations. You would say basically this would be like in context learning. but not limited to just prompting in context learning, but trying to build associations between objects, and then asking if you would have an app operator, for instance, for fuzzy equality, as we talked about, right? So when you do a fuzzy equality between multiple objects, you show it in context, multiple pairs of these objects, and then you would ask it in the end, I don't know, the next question is it what could be an equivalent operation, like is pi equal to 3.1415 dot dot dot, for instance, right? So this would have been like one of these operations, then what you would query. And that's kind of the point why you see this huge gap between multiple of these things. It's because we're kind of using it in the more operator-oriented perspective. We're building a lot of associations or multimodality, in the sense of, in the multimodality case, you might, for instance, have to detect the context a priori. So you basically use in-context classification based on full text, maybe, right? So you get a question or whatever is in full text from the user. Then you have to basically select which kind of tool to use. And then you would have, like, in the next step, use that tool. Obviously, we did not evaluate the tools in our, we did not integrate the scoring of tools. We just said, okay, look, here's the answer. But now basically the answer could be, let's say, a HTML representation of a website. And now we try to extract the information from that website and say, like, can you extract me, please, the main summary of it? And then obviously many models get confused. For instance, if there's a lot of tags and, many things that look wonky. So it's basically then they don't understand what to extract properly. So this is like why it's really about this. If you think about it, this instruction fine tuning, and that's very, very important. It obviously also of the models, how many of these different kind of data types and sets they saw. And I would say this all these open source runner-ups, if you want, so even if they're compared maybe on one specific or the other specific benchmark, if you put them in a multi-step generative process and then ask them a bit like out of their comfort zone, to understand associations between objects, or to understand the context, the classification that they have to like do right now to get the right tool, which is kind of extrapolating a bit out of their perspective, then they kind of, don't really succeed, as you see. Compared to, let's say, GPT-4, for instance. And even GPT-4, if you like, you see that on one axis, this is usually the in-context learning axis, what you are familiar with most of the benchmarks. So here we're like very close up. So I would even say like GPT-4 or Gemini Pro, they're kind of on par on this axis. So I wouldn't make a huge distinction between these two like spikes, but they're basically on par. Not perfect. There's maybe some small variation, but kind of really almost perfect. But then you would say like, as soon as it gets about tool utilization and so on, they already start, if you have too many tools in your context and so on, it already starts to confuse stuff. And when you go into program synthesis, they have to be really precise. They're really good at coding, but like really precise, because it has to compile in the end and really also run. So that's what we also evaluate here. So yeah, this is just to give you a brief idea, but maybe let's start a bit more abstract to really understand how do we actually get to this point? How do we, and what are we concretely comparing?
Yeah, before you proceed, I just have a quick observation. So it looks like, open source models, Llama 2, Mistral, Zephyr, did quite poorly on your benchmark. So
Yes,
it means that perhaps the performance that's reported, they could have like trained extensively on maybe the benchmark data. And so when you do out of distribution, it doesn't do that well. So like,
exactly.
I mean, people are using like those kind of teacher forcing, or like basically using GPT as the teacher and then learning from the input output prompts to fine tune. That has its limitations because you only learn a subset of the original model's capabilities. So
Exactly.
I think this is a good highlight that like it is good only in certain areas, but once you go outside of the training distribution, it may not do that well. But for
Exactly.
closed models like GPT-4, GPT 3.5, Gemini Pro, maybe, they are trained on a very extensive data set that is closed source. So
Exactly.
maybe that's why they could do out of distribution better. I mean,
So
out of distribution to them maybe it's still in distribution because their data set is huge. Yeah.
I would also say that, like, maybe not out of distribution, but I would say, if you think about it, if they have trained like on a lot of, different data sets at once, I think that this just shows the general how uh, well they generalized, basically, because it basically just shows that you now can, even if you have two, let's say, imagine it a bit, it's oversimplified, but imagine like two vectors pointing in space for two different domains, if you want so, right? And then you would basically ask an associative question, if you want so, and try to like interpolate between those two domains, between those two subspaces, if you want so. Then you would basically, you can easily interpolate with or at least proficiently enough interpolate with these like first three models, GPT-4, 3.5, and Gemini Pro. Whereas if you look at Llama or Mistral, because probably saw a small subset of the dataset, maybe generalized a little bit poorer from the weight space and so on the target tasks, or even just try to fine tune, specific parts of a data set, just by copying, if you want to, also because sometimes they also do basically cloning GPT-4 answers and trying to just to fine tune to that, right? So if you just do that, then you basically are still not generalize properly, and you might have the same problem right now where we say like you have two subdomains, if you want, or two domains basically pointing to like two vectors in a direction, but then you try to interpolate between them, and then it collapses somehow, or it just is really off, and really feels more like extrapolating for them out of distribution than interpolating between two domains. So this is like how I would attribute this, but this is obviously a kind of a bit of speculation and just thoughts about
Interesting.
it.
So how do you mitigate like the randomness of the LM generation when you compile your results? Because like there's a temperature parameter for, and then like sometimes your tokens that you come up with the same problem might be different. So how do you do that, like to cater for that in the
I
eval?
mean, we followed basically the settings that were recommended and are basically defaulted, and in the different benchmarks where they say like, look, current version I think of GPT-4 also has a temperature of, I think 1, or is it 0.7? I forgot now the
0.7,
details.
the
Yeah,
default.
exactly. So it's basically we kind of looked at different benchmark. We looked at, I mean, we tested it also a bit like quality wise, and said like, okay, let's stick to the defaults of different papers, how they recommend it, because it's a lot to also do our heavily hyperparameter search and so on for all these models, because the problem with exactly this API based things is, well, they cost, right? The more you probe them, and we had a restricted budget on that front. So yeah.
No
So
worries. I'm sure you can do
yeah,
more expensive next time.
yeah,
Then
for sure.
the other question is like how big is the eval data set? Like
Yeah.
so like roughly know the scale of like if you want to run this benchmarks, like is it easy for people to run? Or like
Mhm.
so how long do you take to run? I mean just some idea.
It takes roughly a day or so. I think
Oh.
that's feasible. That's feasible. So half a day to day, I would say that's feasible, but that's not the problem. It's more the costs also a bit. Like, I mean, sure, I mean, when you have everything set up, everything works. It's not so expensive. It's like maybe one run gets you roughly around 20-ish euros. But obviously, developing it was, well, you burn many times 20 euros, right? It's like so
I
it's
understand.
like
Yeah, the
it,
development process of it, you need to keep trying new things. That's what I also did for my
yeah,
own frameworks as well, the agentic
yeah,
framework. I keep trying and trying, and yeah, I understand where you're coming from.
yeah.
Yeah, so maybe just to delve a little into your thought process behind this, like what made you decide on these five aspects? Like, is that something you see very often when you do your agentic programming with using symbolic AI? That's why you came out with this. Like, what was the inspiration?
Exactly. It was based a bit obviously on also the first part of the paper. So, we looked at in context associations. That was also kind of like we looked at like operators and methods, especially if you want to like make compositional, multi-step generative processes. And where is it? Function composition, as we call it here, right? When you have like different nodes. So we said like, but if you do a function composition, how do you know which function to use? So that was kind of the choice of like in context, detection, and then you've also like classification, where you have to select multiple different functionalities. Then there's obviously the domain invariant associations that we also talked about here, because if you equate two objects, or if you create operators where you say like pi, the symbol pi is equal to 3.1415, and so on, dot, 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 then this is, if I would tell this a human, you would like say, if I use the Greek letter pi and show you that, then you immediately associate that usually with the, obviously the mathematical symbol. So you would basically, the humans with 1-2 examples, they create these associations in their, from experiences, obviously, in their mind. And the idea was here, is there some equivalent? And that's kind of one of the, I would say, most interesting parts of also what we analyze with our framework and do here, because right now there is like little research on how can we create proper abstractions, associations, and compositions, basically, with models. Imagine you would just have 2 samples or so, and then I'll just give you 2 samples. How would you do this with a large language model, for instance, or with any like neural network based model to work with these things? And there are obviously some research papers that do this. But we also said, like, is there a general purpose way to do this? Like, you could give it 2 samples, now it has to memorize those 2, and every time, even if I start continuing a conversation a different direction, and I come back later, much later, and I say like, what was it exactly if I use this symbol? Well, it was this result, right? Because it was associated to something from your memory, right? So that's kind of like the ideas where we looked at associations, where we looked at function composition, meaning detection of different contexts and functionalities. And then we also looked at program synthesis specifically, because program synthesis itself is where you kind of generate stuff, but usually when you generate stuff, you want to maybe visualize features, you want to create, I don't know, bindings to APIs, you want to connect to other objects and so on, and frameworks and so on. So that was actually where we know that like like program synthesis is like basically the one of the key pillars if you make that work, then you can generate stuff all the time in all different directions of languages, interpret different languages and algorithms and so on, and then port that over. And then obviously when you stitch everything together, and you say like, what is the most coherent thing that we were interested in, is obviously logic, and having now this multi-step computational, like basically having these computational graphs or multi-step generative processes. So that's exactly how we came up with, these categories, where we said like, look, logic and multi-step or computational graphs basically are kind of the result out of this, what we call here basic capabilities, which, don't get me wrong, it's not so basic to generate code that works, right? But it's the idea, like everything that falls below here is kind of like building on top of these 3, if you want, to pillars, because if they don't work properly, then you don't expect that anything down here would work much better. So you could see like the 3 axes on the right, top right, and so on would be like,
Yep. Corresponds
yeah,
with your basic capabilities in the symbolic AI.
exactly. So that's what
Multi-model
we.
binding and program synthesis is the code generation part.
So
Oh,
that's kind of like how we saw it. And logic here, as you see it, was then because like we didn't want to ask it like just the Einstein puzzle, for instance, because the problem here is with also current
sorry,
benchmarks that
what's the Einstein puzzle?
so where we have basically just a textual description where you say
Oh,
like
is it the like 5 houses, 5 people, five
exactly,
animals
where
living
at the end
attached?
is like, and who has the fish or whatever, right?
Oh, okay.
That's the final question, because you
Did
kind of like
Einstein come out with that?
uh, uh, no, I think that there's a more general way how it's called. The Zen part, what was it called?
It's some
I
paradox,
forgot.
right? I can't remember it. Yeah, but it's a logical puzzle where you need to eliminate your
Exactly.
options by saying like, oh, if the dog is in house A, then it cannot be in house B and C and D. Yeah. So that's
Yeah,
a
exactly.
traditional
Exactly.
logical test. Actually,
Exactly.
just to pick your mind a bit, do you think humans we think using logic in terms of like when we make decisions?
For sure. I believe for sure, because that's kind of one of the hardest things that we're still having to figure out. So, I mean, what is logic and how it is represented? Because we obviously also, human brains are in a way, you know, electrical signals, impulses, which are kind of gradient ways, but at some point discretized with exchange of impulses and so on. But the question that I'm always, or the thing that I'm thinking about here is, there is like logic can emerge, I believe, from statistical representations, but it has to have like fixed points, in my opinion, where I would say like, when you have, let's say, a description of, let's say, even pi and so on, right? When does it become logical for you if I would say pi equals to 3.1 it's like a probability mass, kind of amasses, right? The more I give you, the more information I give you, and at some point, this if we want to symbol, basically becomes for you very dedicated that this is the mathematical representation of this constant, basically, right? So the idea here, what I'm trying to say is, how I see it at least, is I think logic in a way is sort of like with high confidence probability masses or fixed points that you kind of build up then these relationships in between, right? Where A is associated to B, and then you basically imply and have an implication basically to some C or whatever. But the question is always, is A and B a valid assumption, right? And is the association still holding? And this is oftentimes when we do with math, and then we say like we use different theories and so on, right? I mean, oftentimes we're confronted with the choice, is this now the same thing, right? I mean, when you do a paper, for instance, also, right? And you choose your theory, then where you say like, maybe this is related to my method that I'm doing, you kind of have, it's not there's not like a logic gating and say A, B implies, yeah, that's exactly what I'm doing right now. It's like, well, this works in this paper, this associates this things together, there is the theory applied in this paper with high confidence and probability, kind of, you would say, well, then it applies also to my use case here, right? Because it kind of, and then you can use the same formulas, then you do all the implications, all the derivations, and all the, you know, structured way of manipulating the symbols. But if it doesn't, right, because you just misinterpreted some of the wording, some of the, you know, details, then it basically, the theory might fall out of your scope, right? So that's kind of, in a way, statistical, isn't it? I mean, you kind of interpret it that it might be applicable to you. Obviously, the manipulations themselves are just fixed rules that we kind of merged, rules that we kind of discovered work based on some axioms and so on, right, that we defined. So the question is, how do you get from statistical or probability distributions to finding the right fixed points that you can do these rules and then just apply the mappings, if you want, so, and the transformations. So this is kind of how I see it. I
So
don't know. Does it make
I
sense for you?
I do
What
have
I'm
a
trying.
different view of logic. I do
Mm-hmm.
think logic is a little man-made and artificial. Like the
Mm-hmm.
human mind might not operate on logic because, like, honestly, it takes a lot of training for someone to say if X then Y, you know, that kind of thing. Or X implies Y. Those kind of logical statements are hard facts. X is a discrete symbol. It cannot really be a fuzzy kind of thing because, like, if it's fuzzy, how do you know whether X is true or not? I mean, that
Yeah,
is
but
not.
that's what I'm trying to say. That's the mapping. That the mapping to the facts, or to these rules, if you want. So that's kind of where the probability is kind of for. But I would say these statements make sense in the way, because what we're trying always to find is, like, as you said here, there exists X such that X fulfills Y, right? Because we're trying to find out what are patterns in the world that are like, with one statement maybe, or with a very short statement, applies on many different problems, different situations. So what rules apply, and I think this is like what emerges, right? When you do many of these abstractions and pattern finding associations, then you find out that there is obviously an underlying, just, you know, logic, underlying structure, if you want, so that you could just blank and then fill in basically these two blanks, and they kind of imply, or, you know, exclude, or whatever the situation. The question is now, how do you map to X and to Y? Because this is the very abstract representation of it, where you have these blanks, if you want. So the question is, well, is the blank X and the blank Y, is it representative to what I'm doing right now, right? Or to the situation that I'm trying to model right now. So that's where I would say the probability falls in again.
Right. So actually, I agree that logical representations have some use in very clear-cut, well-defined domains like math. I mean, you have Lisp, Prolog, all these logical solvers that could solve things that are already discretized and have fixed rules and relations. But that is actually not how the world works. Okay, that is artificial. It's like you convert the very chaotic nature of the world into an artificial realm like math. Then you can apply this logical stuff. So I do think that it's useful because there are some cases that this logic would help to lead to a rational conclusion, and then you can skip all the exploration. But I wouldn't say it's the default for the input modality. Like by default, I don't think we have this basically fixed structure where everything like follows like X implies Y. What will likely happen is that we will form relations based on what happened at the time before and what happens at the time later. And then like based on these associations, like for example, me drinking a cup in this room versus me drinking a cup in the office or at school. And the action of drinking a cup is the same. So somewhere in your memory, you store that. And then you could retrieve by association when you're drinking a cup. Next time, you can retrieve what you have done in the past, your experiences and so on. So that's my theory. Okay, I'm not saying that this is wrong. I'm saying that
No. I get it.
yeah, mine is a
Important.
mine is more broad encompassing thing that encompasses like all of what you experience in your life. And some parts of it, if you can say that, oh, this is a cup, I drink from cup, then that could be a logical statement where or like basically some form of okay, I don't know what they call that in lips, or basically if you have X contains water, is that relational statement. I don't know what you call that, but basically you can form this kind of relational statements if you already have a predefined set of objects, predefined set of relations. It's like knowledge graph. I mean, people have tried to codify knowledge into a knowledge graph. It doesn't scale. Yeah, the number of objects is just too much, number of relations is just too much. So to me, what scales is like if you have some form of a fuzzy way of representing stuff like an embedding, you have multiple representations of the same like object or activity with multiple different embeddings of different contexts. Then you can do your matching at inference time. Like at inference time, given the context is like running, then I can see whether a pair of shoes and socks match, or like maybe like if the context is school, then whether like an eraser and maybe a chalk match, because like at school you see both of them. But if the context is not school, then it doesn't match. So I don't really agree that there's one fixed set of relations between objects, like in a logical statement way, because it all depends on the context, it all depends on the situation.
Of course, but don't disregard one thing. There is also like all these mathematical constants, for instance, are kind of also, if you want, so by abstraction, because a lot, obviously some information gets lost. That's exactly what you're kind of saying, right? Because you have the sub-symbolic representation, the embedding, if you want so, and then you collapse it to some symbol, right? That there's like a wave function collapse, if you want so, right, at the point, right? So you basically collapse it on one item. The question is, how sensible is this collapse, right? In the which situation? Because this is kind of like the idealism, if you want so, the ideal space, if you the concept space, as we talk a bit in the paper about it. But then there is still this interesting thing, because if you have this concept space and do some mathematical manipulations, oftentimes then what comes out as a result is some constant, be it the Euler number or be it pi or something like that, when you do this mathematical transformations and so on, right? And geometry and other things, right? So in a way it is valid. There are some natural constants emerging from the objects that we kind of like abstracted to, right? And then do the transformation. And when you see also, like when you do in the abstract space, the computation, because that's kind of all the papers, theories, everything that we built up the last X years, right? Apart from all the empirical search also in the space, right? But if you look at that and then just map it back, if you want so, if you map it properly back to your, let's say, neural network, these abstractions, then you kind of see that the formula and the transformations, the normalization layers, all these things kind of work. That's kind of the beauty of it. It works, although there was some information lost, right, when you did the abstraction, but then you did like the transformation, all of that, the math seems to work when you ported them back to even the continuous space in some situations, right? obviously with some heuristics, things around it. There's a lot, right? Where we know that we have to make this work in very small numbers and yada, yada, yada. So basically all these details that always matter. But it is interesting to see that there is some connection between this abstraction, which is very, kind of lossy of information and idealized, but then back to always the reality, which is a much more just complex thing than just the abstraction space.
Yeah, I'm not saying that logical statements are bad. I mean, it's useful, but it's just exists as a different abstraction space. I mean, there might be many abstraction spaces. Sometimes to solve a problem, you go by association. Sometimes you use logic. But actually, in the symbolic AI framework, the symbol that you have is actually not a fixed symbol per se. That symbol, if it's like a word or a series of words, can also be matched by embedding, right? You can convert into an embedding and
Exactly.
compare, like the number three can be compared with the word tree. So
Yes.
there's already a big difference in symbolic AI compared to traditional logical statements, is that the
Yes.
symbols are very flexible here.
Yes, exactly. So that was kind of the idea, but because there's also maybe to reiterate on that, what we call like large language model, we call them explicitly in our paper like semantic parsers, if you want so, right? Because the idea is like based on the context, that was kind of what was missing up until the 80s, 90s, and so on. It was like missing to have a more flexible way of, because you had just this rule sets, right? Where we suggested like if this happens, then I do this. If this happens, I do that. But like this cascade of rules basically doesn't really scale that much, and it's not so flexible. Because what if you just have a typo in there, or what if you have multiple? Then you can find many hacks like regex to avoid that typo interpretation, and but just the hacks then start to overtake basically the actual thing that you wanted to build as a rule set. But now with large language models, it's kind of like binds these two words really nicely, because they learn just a lot of a huge corpus of text basically, and found the patterns in there, right? There are mathematical patterns, code patterns, there are language patterns, and so on. And now they have this flexibility of association, so the semantic flexibility, right? Where you could say cat, kitten, or whatever at a variant of that, as long as it is still within the closeness, as I said, like within this probability mass of being a cat-ish thing, right? So that's kind of how we see it. And then you can basically collapse it to a symbol, do the maybe conceptual manipulations, and then come back and then basically transform it just with the appropriate function of approximation or whatever it is to maybe get, or with an embedding model to get again a symbolic sub-symbolic form, right? So basically that's kind of like how we see it with the framework.
Understand. But actually in the eval, we move back to the eval. In the eval, the logical eval, are you purely evaluating logical statements in the traditional math sense?
No, that's what I wanted to say here. So that's kind of like the difference where we said like if I just ask it the Einstein puzzle, for instance, that who has the fish or so, the problem what we saw immediately was like, uh, what if it's just saw it from the internet, right? GPT-4, for instance, what if it just memorized it, right? So there is the one pattern, or you just saw even the puzzle itself online, right? And probably it did, because you can just ask it directly and it will give you the answer, whoever has the fish, right?
Yeah.
The German or whatever, right? So but the problem is like, how do you now abstract from that?
Change the names.
Yeah, sure, you change the names, but what if there is like just plug in replacement like X, Y, Z, and it just basically just plugs in names, and it knows if it's on this position, then it's always the answer, right? What do you do? Then you have to change the formulation, and you have to come up with new puzzles, and it just becomes, from one step to the other, but becomes more and more complex, and you have to basically redo all these puzzles multiple times to really see if it works. So what we came up with, the idea was like, what if we just say, can we not just, let's see, if it understands logical combinations within this, can't we just port it from one space to another and keep the relationships, basically? So the idea was like, if you have the textual form, right, can't you just transform that to a code form, where you could use, for instance, Z3, for instance, right? And then do the like really the symbolic manipulation, get a result, and come back to the actual textual space again, and just say like, just restate the answer. So that was kind of the idea. Or where we said like, what if you would have one language the more maybe easier to understand analogy to this would be, what if you would have a code in Java, for instance, and you want to have that code from Java ported over to Python, but not just one-to-one, but the question would be like, what libraries would I have to reuse, right? Because it's kind of like there is not a one-to-one mapping between these two languages. So the idea is there's a logical concept space that the algorithm that is representing the algorithm or the implement, but you just see the implementation of it, right? So can you basically port over or abstract to the logic and then port it over to the target domain if you want, so which would be a different language.
Interesting. Maybe you can show an example of that later. So
Yes,
this is actually quite an advanced test, right? You're not testing basic logical abilities. You're testing also
exactly.
logical
Ex-
plus association, right? Because you also need to.
Exactly.
So this is actually a harder test than the association test. And I would say
Yes.
that even GPT-4 did quite poorly. I remember like
Yes, yeah, it's on all of them did poorly. One thing to maybe keep immediately in mind, but I'm going to talk about this score, what you see here in a second. But the idea is this is a score, which is not linear. So it's not highly non-linear. We also say this in the limitation section. So you wouldn't say like at 0.5 it would be like 50% good or whatever like that, because that's not true. It would be something like from 0, which is totally random, that what we see here, at least from the evaluation, to 1, which is a perfect match of the distribution or of the um, basically reference data set. So and everything in between is basically because of embeddings and because of representations and so on, highly nonlinear. So when you see this, for instance, this axis here, they're basically all of them are kind of just same poorly performing on this spike. So that's what I wanted to basically say. Here you see at least some differentiation here for in graphs, for instance, because there is some statistical representation as in associations. So that's why GPT-4, for instance, kind of differentiates itself and Gemini and so on from the other models. But in this case, kind of all of them are very poor, if you
yeah.
want. So
Actually, why this is a design choice that I would like to ask now. Why not do those hard truth or ground truth benchmarks where like maybe MCQ or like generate like a fixed word, they compare whether the word is correct. Why do you decide to do by, if I'm not wrong, is by embeddings, right? You take the generated answer, you compare the embeddings with the ground truth answers embeddings, and then you form like based on the distribution of
but
like how far the embedding is, you get a score, right? That's what you're
yeah.
doing now, right? For Vertex, for this.
Yes, exactly. But the point is exactly in that, because you don't want to memorize one answer. You want to see if the overall answer set. The problem often is like when you ask it for summarization, for instance, there is not one answer, one summary that is correct. There is a set of summaries that are all equally, because one sentence could just be beforehand, starting differently, having different words, but all of them would be valid. So we don't want to collapse to one representation and say like, look, this is the only answer you could have given me, and this is the only correct one, right? But there's like a set of answers that we are interested in. So that's a distribution of answers, if you want to, right? So it's not a unique solution, but it's a more a distribution of solutions, right? That you're
I,
looking at.
I do like the idea of using embeddings to like distinguish between similar answers so that or different answers so that we can accept more varied responses that all mean the same thing. I think this is a limitation with like current measures of benchmarks. Like okay, MMLU uses MCQ, so the one is okay. But like if you want to do like sort of summarization or extraction benchmarks or question answer benchmarks, sometimes the answer is not the same. So what people have done is they use NLP methods, natural language
Mhm.
processing methods like the Rook score or the
Mhm.
score, BLEU score, and
Yeah.
those I actually don't. Actually, both of these are poor metrics because they don't capture the essences of the text that well. They just see whether the words are the same, the longest common
Yeah.
substring, that kind of stuff.
Exactly.
Yeah.
Exactly.
So I like this embedding method more than those existing methods. But why not go even further? Why not use a large language model, take the correct answer, and then take the generated answer, and then you give it some options like is this semantically similar, or is this not semantically similar but close in some domain? So you give it like a classification, like classification 1 could be very similar, like exactly similar. 2 is not so similar,
Ye-
3 is not similar at all. Like you can ask it to classify. Generally, it does quite well for like
mhm.
ChatGPT when I tried this out. Like why not go this approach? Why use embeddings?
Because they're like, so there's like basically 2 versus 1 problem. Maybe let me elaborate on that. So your first assumption is obviously that the one model that you use then has a proper understanding of the questions and the context and of the evaluation, right? That's the first assumption. Now you might say, okay, but that's the same with the embeddings, right? It has to represent properly your, your symbolic representation in a sub-symbolic form that captures all the meaning or the highest parts of the meaning. True. But the second problem of the first method is now you also ask the model, does it have a proper understanding of a relational, like mapping this, textual form to a scoring, which means that you're kind of assuming that the model already has a proper way of quantifying or weighting it, right? Which even we as humans have problems doing that, because if I would just give you two sentences and say like, look, they're kind of similar, but which one has a score of 0.9 and which one has a score of 0.5 or 7 or whatever, right? Or is it 0.7? Is it maybe 0.6? Is it 5? Is it, like the problem what emerges there is like, what's the number? What's the number you would give it properly? You could just rank. You could just say, I prefer this over that. And then you just have ranks. But the problem is ranks are already an abstraction again, if we talk about, as we talked earlier, right? So you say like A or B, like I prefer A. But now you need a lot of examples to get from ranking basically a continuous value again that reflects that actually property that you're looking for, right? So that's why I said like there are 2 problems basically that you're facing with using an LLM. Maybe the third problem even would be now you can't use that LLM anymore for the evaluation, because you're kind of using itself to evaluate itself, which is kind of, you probably would have had GPT-4 in mind, right? So you would use maybe GPT-4 to do this kind of evaluation, but then it would be felt kind of unfair if it would critique itself, because there might be some inherent biases in there, right? When it prefers its own distribution, right, over others. So that's kind of like where we said like, no, is there a more let's say general form of doing these comparisons? And there was also the idea like, is there a way, what if I don't have access to the logits and because that's the kind of problem with what we have with these API based systems.
Yeah, closed source, they don't give you logics.
Exactly. So you don't have logits, you don't have any like latent representations of that. So how do you do that? So that's why we said, look, there is a actually more general form of how we could do this comparison. And we could basically just use an embedding model, held out embedding model, which was properly trained, but has no connection to all the other models, if you want, so no direct connection at least, right? So and use that basically as a held out model, which we never tune, we don't change. We know that it's not perfect. We know that there is a high nonlinearity in the representations. That's why I'm also saying here in the score reflected there is some nonlinearity, but that's the trade-off. At least this is monotonically increasing. We did some empirical evaluations. We saw, okay, we when something is closer to the what data set that we wanted, there's always a monotonic increase, or at least on par with the previous score if it didn't capture the nuance, right, of the change. So it was basically good enough to say like, look, this is and this is actually what we want. And it's also in a nice way, because that's kind of the connection. Maybe also let's come to a bit from the theoretical part. We saw this connection very inspired from the Fréchet inception distance paper. So that's exactly where we kind of saw this idea and took this idea further, because in the with the Fréchet distance, basically you have these 2 distributions, right? Where you have basically a reference distribution and the generated distribution from your model. And you would say, actually, can we, just match, if you can bring the the generated distribution closer to the reference distribution, then we're basically getting from the same data distribution the results, right? And we said the only difference right now is obviously that it's not just one generator, it's not just one step. So it's not just you have a GAN if you want to, because that's when it was introduced, right, with that back then with GANs. So you had this GAN, you had all this problem with mode collapses and other things, and you
I'm not a fan of GANs, by the way.
Sure. But also back then we had like, there was the problem, how do you evaluate the quality or the nuances of the qualia, if you want, of the picture, right? And the idea was like try to bring both distributions closer, like the generated one to the reference distribution. And that's kind of what we did also here. And so like, can we do that? Can we like, have a reference? That's why it's in a way supervised what we're doing, right? So you basically have your workflows that are interested for like what you defined a priori. You said like, I have this, and this that I want to step through. When this happens, I want to use this tool. When this happens, I want to use the LLM and so on, right? So you kind of have this reference thing. And now when we generate stuff, can we like see how close are we to what we have expected to get, right? And the problem here was then obviously when you look at obviously distributions, so if you would try to get this multivariate normal distributions, you would have to estimate like the mean and the covariance matrix out of that. So that's kind of like, we tried some examples, but the problem is estimating these parameters. You have to use a lot of samples, right? And you know how it is, right? I mean, generating now 1,000 samples with, let's say, with GPT-4 to estimate this and that's not even profound if you want so, right? And now having a multi-step generative process chained together, like in a compositional form, right? And I mean, this becomes easily infeasible. So we said like, okay, that doesn't work. It's in theory, yes. In theory, this would be exactly what we want to have, right? Every node is basically one of these distributions, and we just compute the integral basically over all these nodes, and then we have the multi-step generative process mapped, and this is basically our computational graph, and in the end we get a final output distribution for what we care
This
of.
is the theory of what ideally
Exactly.
to do, right? But this is not what was done, right? Because it's
Obviously, you have to.
intractable. So this is the problem I
Yes.
have with GANs also. Like probabilities are so hard to train. They're intractable to sometimes. And I mean GANs had an even worse problem that the training objective was like is either the discriminator saying yes or no to, so there's a
Mhm.
binary learning signal, which is very bad, like very hard to learn stuff. Okay, but that problem is not here in this Pratchett distance because it's purely
Mhm.
comparing two distributions.
Exactly.
Yeah,
Exactly.
but
Fully correct.
why Pratchett distance though? I mean, like there are other ways to compare different distributions. You could just
Yeah.
like Earth mover distance or like with your
Yeah. Yeah.
distance.
Sure.
Why
But
do you want this Pratchett
we
distance?
looked. I mean, we looked and like the next question was like also with the experiments that we did in parallel, like we saw like the embeddings. How do embeddings really distribute themselves? And they are normally distributed. Like I mean, like if you look at the points and you just map multiple ones, and so you can get this bell curve because they just have a lot of numbers mapped around close to zero in a Gaussian way. So it then became really very natural. We would say like, look, I mean, this is kind of like what we saw. I mean, maybe I also have some bias from my lab if you want so, because this is also where it came from. But
So your
it
lab
was
does
basically,
Pratchett distance.
yeah, exactly. So this is where,
Oh,
so
nice.
but the point is like I just looked at it and like said like this is kind of what we're doing here. Exactly that. Even if you think about what I liked, as you said it right now, you had like in a discriminator scenario, you have like A or B, like is it this or is it that, right? Fake or real. So in this case, it's also like we have a symbolic form, just more tokens if you want so, right? Just much more tokens obviously, but it's kind of also like which one is it, right? Which kind of the discrete tokens is it in the end if you would map it back to a discrete space. So I saw a lot of similarities here, so I felt like
Can
this
I
might.
ask like
Yes.
how do you get that distribution? Let's say from the answer that the LM gives, like this is a
Mhm.
person or this is a dog. I mean that how do you get the distribution to compare here from just what the LM produces?
From what, yeah, that's more concretely down here because we use obviously kernel methods to do this embedding, to do this mapping. So when we do so we obviously use you have dog, you embed dog basically
Sorry, before we move on there. So this Pratchett distance is basically just a distance measure to see how far two probability distributions are from one another.
yes,
So then the
yes.
next question is, you're saying that the LM outputs look like a Gaussian, look like a normal distribution. So my question is, how do you get this normal distribution from the LM output? Yeah, so that's what I
Like I said, you would have to have multiple samples with multiple variations of the same like concept. So if you want to know is it a dog or a cat or whatever, then you would have to write dog maybe in a small small case, like lower casing, then caps, all caps, then maybe a variation of that, then maybe something related to cat, whatever, kitten, and so on. And right, you would have to have all these mappings to to have the full distribution if you would really want to get the distribution of a dog thing, whatever a dog thing is, right? Maybe even in the context of a sentence or so on, because many words are not just single words, they're also associated to the context surrounding, right? So that's why I said, like, it's really infeasible to get the full distribution if you wanted to have the full distribution of the object. So the
The
most
distribution,
sensible,
you mean token distributions?
yeah, I mean token, exactly. But below the tokens, tokens is basically you sample already, right? You discretize the problem already, because you kind of, I don't know, take top P or whatever, and then you take
Yeah.
only from those, and so you kind of already discretize the problem. But imagine you would have the logits below, right? That's kind of that's kind of what you see here. It would be like you go from the logits below, and then you look at the distributions, if you want, of all the logits forming the object, if you want. So, but like I said, many models don't give you the access to these logits, to the distributions of the symbolic layer,
I see.
because of the
Also,
APIs and so on.
it's something like a sequential thing, right? So you take the first token that's generated, you see what the subsequent tokens are, like 20% token A, 50% token B, 30% token C. Then you go to the next step. Next step. If let's say token A was generated, what are the possibilities? If token B was generated, what are the next few possibilities? Token C generated, what are the next few possibilities? Then
Yes.
you basically keep repeating that for every single trajectory in your graph there, and then
Yeah,
eventually what you
exactly.
get is you get a distribution of possible sequences of
Yes.
tokens. So
Yes,
if
exactly.
let's say
So,
I am a dog, I'm a cat, I'm a person, so let's say you have 1,000 different generations, and I'm
mhm.
a dog appears 50 times. So that would be
Yes,
a distribution with I'm a dog at the center here.
exactly. And then you spike basically what it is in the end, and everything else becomes heavy-tailed or whatever
So you are
around it.
saying that if you let the LLM generate a sample output X number of times, let's say X is 1,000 times, by observation that when you, let's say you generate with a different random seed or different temperature each time, or I mean high temperature each time to get multiple diverse generations, what you
Mhm.
are saying is that you have empirically observed that the prompt that comes out, or rather the output that comes out, the sequence of tokens, is more or less like focused on only a few as the more common ones, and then the less common one becomes like more like a flat tail,
But
long
yeah,
tail.
but it also makes sense, right? I mean, it's when you're prompting it. I mean, if you say like in context prompt, right, and you ask it like a specific question, you kind of already create a subspace. You already say like, I don't care about all the other. I know you know probably about microbiology and about quantum physics and all that stuff, but you're not asking about that, right? You're asking in this moment, can you do a poem, right? So it basically collapses everything away
Understand?
that has even like all the Greek letters, if you want. So, right, everything around which is not related to it suddenly disappears, right?
Correct. So
Uh,
that's my next question. So when you do this probability distribution, your base, or rather the domain you are on, needs to be the same for both distributions so that you can compare. So that means like the x-axis, if you will, like I'm a dog, I'm a cat, needs to be like similar for both distributions. So like
yeah,
large
yeah,
language
the
models,
support, yes. I mean that's
okay, yeah, that's the word I was using. The support must be
yes,
the same. Yes, sorry, not the domain.
yes,
The domain is the result. The support must be the
yes,
same. So
yes.
the thing is, for large language models, you have a lot of possible generations. Then how do you ensure that your support is the same?
That's actually even nicer now way if you think that your support is basically the token space,
Oh,
or
that's huge, the
if the
token space.
symbol the symbolic space, because that's when you use a post model, an embedding model as we used it here, right? Because we said, okay, maybe we don't have access to the same, we don't have access to the logits and all that stuff from every LLM, and as you just pointed out correctly, every LLM might have different architectures, a bit like different in logits and so on. They vary, so you
In
don't
fact,
have the
their
same
tokens might be
support.
different also. Like
Sorry?
the tokenization might even be different. Like like
No. Forget token. Sorry, I mean symbolic form. So meaning text. You just look at the text. All of them, you assume you have Unicode, whatever is your
yeah.
support in this case, and then basically you just take a reference model. That's why, like we said, we have this embedding model, MPNet, for instance, and as long as it can always manipulate all these, symbols that we are using here and encode them in a sensical way, then you have the same support always, right? So that's how you can map all of them regardless of the underlying architecture, what generated it in the end.
So you are mapping it by symbols. So like, but
Yes.
the symbol, are they word by word or the entire generation as one symbol?
So in this case, it's like every node. So as you see here, there's basically this integral. So you in the theory, again, as you pointed out, right? The theory would have to like take every
And
follow
if you
up
go every
token,
step, right? Yeah.
and exactly, and then integrate over each gradual step, time step, and so on, right? But obviously in practice, that was again infeasible, right? I mean, how many steps? Think about when
And you also don't have the tokens. I mean, you don't have the logics. Even if you had the logics, it's also intractable.
Yes, exactly,
Yeah.
exactly, exactly. So you see that there's a problem. So what we do is basically, as we call it down here, we do Monte Carlo approximation, where we say there are some fixed points that we're looking at, and this is exactly the nice part of it, right? This is exactly reflecting what we do in reality. You have an LLM, you kind of prompt it in a way to give you a result, and then it has a halt token at some point, right? Because it kind of auto-regressively
Yes.
generates something, and then it stops at some point. So and then actually comes back and gives you like, this is my result. So it's basically the entire step that had took like multiple generational steps in between is just conflated to one evaluation step, right? Which the result when the final token triggered or so. So basically, this is and then you even can, and that's the nice part of it. Then you can even like think about using any other more generative process. So you could see a database, for instance, a lookup, whatever, it could be a generative process for you because you kind of give it a query and then something else comes out, right? It generates a different kind of tokens. And the support remains the same because it's all symbolic, it's all text if you want, so right. So you could then even like put in any other be it a solver, be it a database query, be it a search engine or so, because all of them have the same support in the end, and you just have to evaluate at that specific point. Obviously, for our scoring down there, we always said like we're not evaluating now tools. Like we're not putting tool, like if Google didn't give me a good response to whatever it is, I don't put the tool like the Google difference or so into account. But that's why we always said like, did we get to the point to do the Googling, the search engine query? And then this would be a reference that we kind of like every of the experiments got the same reference back and said like, can you now parse this reference and extract the information that you need, for instance, for the follow-up task. So we did just the evaluation in this of the LLMs, not any of the tools.
Okay, so basically it stops before the tool is called.
Exactly. So the tool is just not called. It would be called in reality, right? And it would give you an answer back. And we just said like, what is the answer? What we could get back. We did this for every of these experiments. And when it was like, for instance, as I said, search engine request or so, then we used exactly predetermined, I don't know, parsed text, which you get the entire JSON back or so, which is like a huge JSON with all the properties in there. Or if there was an HTML, like open up a website or so, then we used Selenium, and basically Selenium would give you an entire web page back, right? So we cached obviously the web page and said like, look, this would be the result, work with it now, and all the models got the same results that to be comparable.
So do you actually call the tool, or you don't call the tool at all in your eval?
No, we're not calling.
So
We
you are just taking
we,
the
we just
input to the tool and comparing the similarity based on it.
exactly we're looking at the input of the like, how was the query similar to maybe what we wanted to have, and also how do you process the output, which was standardized across all models, because it would be unfair, right? Just because one has some semicolon or whatever in that query, you would basically
Also, you do like regex to make it standardized, something like that. Some form of
uh,
rule-based
just
action.
just casting an idealized variation, a variant of it. Think of it, you would want in one of the experiments, you have a reference set where you say like, please first classify what it is. Is it a large language model usage? Is it I don't know, usage of a search engine? Is
And
it
so
a
you
usage of
basically, the tool name, you ask it to give the tool name, and you compare
yes,
the first cut whether tool name is the same. And
yes,
your
exactly,
second cut will be whether the parameters to the tool is the same.
yes,
Yeah.
exactly.
But this
Or the
actually
yes.
can be a little unfair, you know, like sometimes the tool inputs can be vastly different, but the result can be the same. Like for example, if you want to do a Google
Of
search,
course.
right? You can
Of
search
course,
a very long
but
query, but a short, yeah.
we're not saying that you couldn't do it, but in this case, we wanted just to see how proficient are the models. Do they kind of have the same results that we would have expected? That's why we'll always say there's a reference distribution, right? Where we said, like, do we get kind of these workflows that we would have expected versus what do we get out of it? So and we kind of wanted to control the variance that can happen, right? Because the problem is whatever input you put into a search engine, you might get, as you said right now, any result back, or just because you have 5 semicolons in there, right? You might get no result back because now the semicolons just overtake. But then, I mean, that was one of the critiques, even what we said here in our paper, where we say, like, if you do it this way, you can do it this way, by the way. But then in the end, you will render every of these models unusable, because that's kind of what it is in the end, right? If you do a multi-step generative process using tools and all that stuff, and you just hard fail and say, like, no, you did not, or just have a hard cut there because now it uses the search engine and the search engine was used wrongly because the query is just way too bloated, right? Then basically from this point onward, every other step anyways fails for sure.
Yeah,
Right.
why
So
not you do
everything.
error carry forward? Like for example, you just do the step one output and you see the input to output whether it's correct for step one output. Then you give the large language model the correct step one output.
Yeah,
And
but
then
that's
ask
what
it
we
to
do.
generate the next step. So you can.
Yeah, no, that's what you do. That's what you always from each step to each step, we just assume and say, like, look,
You assume that
this
all
would be.
previous steps are correct. And then you
Yes,
ask.
exactly,
Yeah.
because you want to have in the end an integral score, which can integrate over the entire workflow and not just because in the first step already, because otherwise all the results would look almost zero, especially for these small for the open source models. If you wouldn't do this basically, and you would just penalize them at the first step, just if they screwed it up once, then it basically all of them would be rendered
Oh,
unused.
no, I'm
Even.
saying that even if the first step is output wrongly,
Mhm.
you feed in the correct first step inputs to
That
the model, then ask it to generate the second step. So that in that case, you
But
don't.
that's what we do. That's what we do. And we account for the deviation of the first step. So we measure the deviation of the first step and then just pretend in the second step when we go further, look, this was the first step result, right? This was the ideal case. And then just go on from here.
Oh no,
And then we do
I'm
this.
saying that you modify even the inputs to the large language model. You will call the large language model a second time, but this time around you feed it the right inputs for the first step.
What would it give me as an advantage now? I'll just call
So that
because now
means
it knows the answer already.
we can evaluate not a multi-step all the way. Like we will just evaluate multi-step step by step. So first, whether first step is correct, and then the second step is given that first step is correct, whether second step is correct.
I see your point, but yes, but that assumes that I see your point, but that assumes that basically everything is in context, then all the
Yeah, you
results,
have to provide the whole
which
context to the large language model.
yes, but that's not the case because that honestly that's not how we see workflows in reality. We see large language models more like central processing unit, quote unquote, where you use it to evaluate instructions, but then you might execute different kind of programs, right? So you might basically end up the first instructions are using it like even in an atomic way, right? So you give it an instruction as an operation, it has to just classify, is it A, B, C, or D? Then you might use the different tools, then do some computation there, and then come back and then maybe use it in a different way, the LLM, right? It doesn't have to be always a chat way of just extending everything in context. So that's how we see a computational graph, because it could be independent even of the LLM. And at some point, if you enter up in a software, you do your computation in the software, all the rendering pipeline, whatever you do, maybe come back with the result, and then basically take it from there. And might be not even that you care about the context at the next step. So that's how we see it in more general way, because you might not care about having all the context or history of the LLM.
Understand. So I take it that this is like a part of the agentic workflow. You are just seeing whether it does the LM generation part to choose the function well. You are evaluating that. But this evaluation just ends there. It doesn't go to execute the tool and see the tool output and compare the two output. So that means the output of the whole process is not compared. We are just stopping at the large language model generation part.
Yes, but like I said, in this case, we cache the results that every LLM gets basically the correct, if it would have done it correctly. So that's kind of how we reply in that scenario. Calling the tool would be just doing more computation, which is like nonsensical, because it would give you some result that you know it's then maybe wrong, right? And if you would compare the results there, you already, if you compare the input, you already know that it was wrong, because
I mean,
it's,
it depends on the function. I mean, some functions you may not
of
know.
course, of
Yeah.
course, yeah,
But if
of course,
the
of course.
functions you use in the eval is like quite confident that like if the input is too far away from the model answer, it's going to be wrong, then I think it's fine. But it again depends on what functions you use for the eval.
Of course.
Yeah.
But yeah, anyhow. So to sum it up, maybe now a bit quicker. So basically, this is the idealized case, as we said, from the Fauché distance, but and integral of Fauché distances. And now we said, like, because I have some background in this direction with some papers. There are actually, you could use kernel methods basically to approximate these, using like kernel mean embeddings basically to approximate the distribution comparisons, basically by using, in this case, embedding samples. So what you have here basically are just two mean embeddings, and then you're using this maximum mean discrepancy as a distance measure basically, and then you would basically compute the integral over these distances of this maximum mean discrepancy
Maximum mean
distances.
discrepancy is like taking the vector, you take each component of the vector, you subtract it and take the square. Is it like a mean square error?
So in a way, it's a bit oversimplified, but in a way you see it basically here. So you would have the norm distances of in a reproducing kernel Hilbert space basically,
Mean square error in
and
Hilbert
of
space.
the in the exactly. So that's
Yeah. All right. It's a mean square error of some sort, right? In other words, but you map it to
yes.
something first before you do the mean square error.
Exactly. So, and actually, that's exactly the point. If you look at this now, um, we even looked then at because we did some experiments also here to see, okay, what exactly do we care about? Because there is one more thing that is a bit annoying for us, because you get distances obviously for this MMD, where you have then, let's say, values like 4.6 whatever, or 6 point, I don't know, so, just distances, right? So you could use that obviously, but to compare across these different models and to map it in a more, you want to have something between 0 and 1 mapped somehow, right? In a scoring, if you want. So
You need to normalize it.
yeah, you want to normalize it, and then, like, you have to, obviously, to normalize it, would have to keep track of it, and
And
have this
probability distributions are intractable, so you don't know how big they will be. So
exactly. So
yeah,
we actually then analyzed just the MMD basically, and just said, hey, is there another way to, if you look again in the section, we looked at basically the components of the MMD, which is actually computing the cross terms, if you want, so versus like subtracting in the end the self similarities to each other. And actually, what we care about is actually just the cross terms. So we kind of oversimplified this a bit, so that we approximated the MMD a bit, very simplified with some assumptions here,
I mean,
where we
this
just
kind
said
of looks like a dot product now.
of kernels. It's basically the Gauss-Carlson kernel dot product in the end.
Yeah.
What it collapses towards, right? With the summarization. So this is kind of like our crude approximation, if you want. So of the MMD,
Does
which
it
is also
bound itself to 0 to 1? It doesn't, right?
yes. No, it's bound to 0 and 1. It is
Oh, it
bounded
is
because
bounded.
there's yes, exactly, because you just
Oh,
plug
okay.
in the Gaussian kernel, which is then bounded.
Oh, I see. I
Uh,
see. Yeah.
and then basically you get exactly this, what we wanted from the start, having something between 0 and 1 bounded. And now we just have to map the symbolic form to a vector valued representation, which is then using MPNet, for instance, to do this mapping. And then we basically just can compute the cross-term similarities with the Gaussian kernel. And we basically get this. And if you do this multiple times, obviously, because you do this not just for one seed and for one example, but you do this for multiple seeds and multiple runs and so on, then you get at each generative step, so at each node, basically, where we have this graphic, so at each node in time where you evaluate something and generate with an operation and some context. You enter your symbolic engine, you evaluate something, get some prediction out, right? Now you symbolically map that basically, map that sub-symbolically, and then you basically always compare to the reference set. And then you get basically this normalized score.
You see, you are doing exactly what I was thinking of. Like you give 1 and 2 as the inputs already and ask it to predict 3. So it's like there's some form
Yeah.
of error carry forward. Like you give it the model answer first, then ask it to
Yes.
generate the next one. And this one is not a token that is generating, it's generating a symbol. So this symbol could be like the next step of the whole agentic chain, like what to call.
Yes,
That's the
exactly.
symbol, right?
Exactly.
So
Exactly.
actually, if
Exactly.
you replace symbols with steps, that will work also. Step 1 of the function calling 2, step 2, what
Yes.
do you
Yes.
call step 3? So this is symbols in this diagram, but it's actually like the different steps of the process.
Exactly, exactly. And then you have this multi-step generative process where each node basically in this graph, in the computational graph, is producing some generative output of symbols, right? So like I said, if you have obviously an LLM, it produces some text of whatever answer the answer to your question or so. But if it is obviously if you're a bit more lenient, then you would say like, can we also use any other, maybe tool and so on as an output, or maybe think about even what if you have like just a binary result, like in a Bernoulli trial, for instance, because this could be something like when you generate, let's say, you do program synthesis, you generate some code, and then you run the code. Did the code execute or not? You could just use that as 1, it executed, it worked, 0, it did not work. So you could even, if you're a bit more lenient to this, integrate into this into the score the process that you were able to execute the code and it produced a result. And even if it can be, if you really a bit more, this is then more heuristic then, but you could even integrate a normalized score of subtree or abstract syntax tree substructure matching if you want. So because code can be also in many flavors and forms as an output and variable names and so on. But if you just look at the abstract syntax tree, then it has a much more structured representation and a much more collapsed version, instead of looking at every word variation and every how you declare the variables at each point in time, because it just looks at the structure of the program. So
Actually, the whole method you described actually is very complicated. Let me propose something and you see whether it can
sure.
work also. So you use MPNet to embed a symbol, right, into embeddings.
Yes.
Right. So I mean you can also use like OpenAI embedding models, but in this case to
Sure.
be LM free, you use an open source model, which might
Yeah.
be poorer in performance, but at least it's invariant. That I mean supposedly free of bias. I mean there's still a bias actually. This MPNet might be trained on some data.
Sure.
Yep. So
But
let's
it's
assume sorry, yeah, continue.
no, just I was just saying like you have to compromise somewhere, and so we just said
Right.
like, okay, I mean, if this is the best performance to speed also trade off, and also the probably most quote unquote most unbiased version
Yeah.
because it's held out from the other ones.
Okay, so I have some issues with that. So I rather use the GPT embedding models because they are more performant in most cases. But let's put that aside. Let's assume that this embedding model is free of bias. Why not just do this? You take whatever is generated from the LM and you take whatever ground truth it is. First, you embed what comes out from the LM into this embedding model to get the embeddings. Then you take what comes out from the ground truth and you embed it to get another set of embeddings. Let's call the LM embeddings embedding A and the ground truth embedding B. Okay, you have two sets of embeddings now, right? Why can't we just do like a cosine similarity and then like that could be your
Oh,
measure?
we also
Yeah,
did a cosine similarity experiment, which we referenced in somewhere here, because we have some like you could use any other kernel, like a cosine distance in this case or similarity. What you're proposing is basically one of the other distances that you could use instead of the Gaussian kernel. What you apply there, but we wanted to keep as close as possible to the MMD to the theory. But you could use a truncated version of the cosine similarity, because why I'm saying a truncated version, because you would truncate away the minus 1 to 0, and you just look from 0 to 1, how you don't care the anti-similarity, because you in practice you never get that, or seldomly
yeah, sure.
actually.
So in terms of the experiments with cosine similarity, is it similar to this MND measure that you're proposing here in terms of the results?
Yeah, the scores might shift a bit, the numbers might shift a bit because
But
of the
monotonically
properties.
is around the same, right? In terms of
Yeah,
the
so it's roughly the same if you would look at
yeah.
the results, just shifted version of it.
Yeah, then my next question is why not just cosine similarity? I mean, it's much easier to understand and like most people know about it compared to M&D. I'm not
Because
sure whether this M&D is a renowned way of doing this, or is it like something that
But
you come up with?
that's exactly what's the interesting part of it, because you could do kernel methods now, and kernel methods have also bounds around them. So if you know, that's kind of what we're trying to propose also with the paper. This would be the most general form of it. Like if you could see this perspective of having this integral over all the tokens and everything that gets generated along the path. But the next approximation of it would be using kernel methods to do this, basically this computations of distances between, and then they have properties, they have like bound properties, and they have other methods, because this in the end is a heuristic, a really crude heuristic if you just take the truncated cosine similarity, which you can do for this particular case, but you might lose other properties and other traits which is coming from the more general concept. So that's why we kind of proposed it this way. And yeah, and like I said, feel free if you feel like more comfortable with this kind of kernel, then you can also use obviously a cosine distance.
No, I mean,
Um,
I feel like personally, okay, not critic on your paper or anything, but I feel that personally using embeddings, you lose out a lot of information already because that embedding itself, it depends on how well your embedder can embed it well. So like two sentences might mean the same thing, but if the embedder is trained wrongly, one might go here and one might go here in embedding space. So you will get a very far distance between the two embeddings. So one thing is a cosine similarity is highly dependent on like the context that how you train your embedder and so on. So I tried experiments where you like just prime the sentence or the sentence with some context and then see whether it shifts the embedding space well or not. Turns out it didn't really shift it that well because the context ultimately didn't really cause the embedding space to shift that much. Like so I would say that
but that's why you need to normalize. You have to recenter and rescale basically. So it's like a Z score if you look at this.
yeah, but this one ultimately is still using the embeddings as the input, right?
Yes, it is
So
used
so, so
the
you,
embedding here, and
you can't
you
solve that
compute.
problem because if the embedding itself is already wrong, then no matter what function you pass it through,
Sure, yeah.
answer will still be wrong. So I'm targeting the embedding itself, not your method. So your
Yeah,
method,
yeah,
yeah.
sure.
So
But
I'm just saying that maybe the better way to do the evaluation will be to use an LM to say, is this similar to that? Because if you use an LM to compare between the two sentences or between the two outputs, desired output and the ground truth output, LM output and the ground truth output, use the LM and do a comparison. And I mean, you can ask the LM to output like 10 different categories, and then that can be your score from 0 to 1. Yeah, that
yeah, but
actually,
that
I think,
again, but you have the same problem. You just assume that the LLM
correct. But
understands what the
LMs,
nuance of your problem.
especially like GPT-4, are quite good at this task because they have been trained on it. Like to find similar sentences, I mean, there's a data set for that to see whether,
I
right?
could see I could say the same assumption about the embedding is trained on all the corpora of data around, right?
Correct,
Because
but embedders are worse than using the LM itself to do the evaluation. I've empirically tested it out, and it's way better if you use LMs to compare directly with the full sentence rather than you extract the sentence out into an embedding. That's why like retrieval augmented generation methods, if you use by embedding, sometimes it performs quite poorly. Like you ask him like who directed the matrix, then the embedding methods might give you stuff about mathematical matrix. But then if you use an LM to do it to compare to the source documents, with the word directed, the matrix, they will know that it's a movie. And then
again, you
yeah,
have to reduct the randomness and recenter basically back. That's why if you have, let's say, look at the embedding. If you just ask an LLM, we had this experiment. Obviously, we said like do program synthesis, and we ask, for instance, Mistral or whatever, Llama or whatever, and then it just produces something in the output where it just uses a variable name or something like, oh, Python, you want some Python code, and just keeps on yabbing about Python, right? Obviously, there is some similarity now between the output of talking about Python versus, well, the code itself that I was asking for in the beginning, right? So, but to counter that issue, what you're just describing, that's why you do a z-score normalization, basically. So you basically have to compute also in this z and this z-rand here. There's also the random similarity, basically, with just some random vector towards the solution. And there is also the similarity, basically, to a reference solution or between two reference solutions, if you want, so to rescale. So when you do then basically this computation here, basically you do this MMD once for the generated output with the reference, and then you have to recenter back by subtracting, for instance, the randomness out of it and rescale it, because you obviously have a different value range depending on what kind of output you have, and this is how you get a normalized final score in the end. So this is how we did it, and this is exactly accounting for what you just described, that you might get some random similarity if you just compare two vectors. And that's exactly why we're not just doing cosine similarity, because just doing cosine similarity has exactly this effect that you described. But if you do look at the kernel of basically this cross terms similarity and recenter around and rescale around randomness to account for that, then you basically get, if you want to, a normalized score out of it.
Understand.
And
Okay, so I think we have talked quite long about this equation. I take it that this is like a better version of just pure cosine similarity. You experimented quite some time. This works better. So let's leave it as that. The exact details of why it's better, because of some normalization of some Monte Carlo sampling. I think that is fine. Because if we go into detail, we might take the whole session already. So let's leave it as that. I will just treat it as the performance measure is fine. So actually, personally, what I would prefer is that if you are doing an agentic framework structure, I would prefer that the evaluation is output based. So it's like whether the agent performs the task well. Like then you evaluate whether the task is done through some rule-based methods and so on. So that is my preference rather than like stopping at the two level. So I can take this that this may be the first cut evaluation. I think you didn't do the second part because the models all failed quite badly. So if the models had succeeded, the outcome of the two use will be quite interesting to see. Like, yeah, but maybe your eval is too hard for the current state of the art models because it looks like it's hard. Yeah.
Yeah, it is difficult. But like I said, we always continued basically the experiment. So we continued with an idealization case where we said like, even if it's screwed it up, we just account for the score that it got, and then just move on and pretend that it would be an ideal scenario again. So this is what you see actually in our algorithm one in the vertex protocol. If you look at the multi-step generative basically evaluation, then you would see that we initialize basically the different engines and so on. We generate, let's say, a plan with the neurosymbolic engine. This could be your large language model or any other plan generator. And then you get basically a prediction of the plan. But you also have here a YP, which is basically the ideal plan. And now you basically evaluate the XP and the YP, account this, basically just aggregate the results and so on. And you have also your scoring function here, as you see, and the embedding model and so on. So basically, you're now embedding this symbol and this symbol. You're embedding them both, and then basically get the evaluation similarity, and then you just move on with the YP. You use the idealized plan because if we just continue with the generated plan, and if the generated plan didn't not even structurally do something meaningful, then from this point onward, the evaluation is anyway stopped already because nothing will work anymore. So that's exactly what we say then, like, let's go from the reference plan, move on, and let's unfold. Then we unfold the plan, and then we start basically until the plan is not like the last thing is like empty, the set. Then we basically start scheduling, and we're now scheduling basically just the next capability that we're interested in, and we're scheduling the next task result. And then we're saying like, look, dear LLM, can you please look at the
Choose
current
the
task.
function, choose the parameter.
Exactly.
Okay, yeah.
Exactly. And then we execute exactly that. Then we get back a result that C, for instance, is a result, and also the task result it predicts. So you basically have the classification of the capability and also the result that it would use. And then we again contrast it towards the reference task and reference capability and so on, right? Where we say we measure that and then we just pretend again and we move on, right? So we schedule and
Oh,
update
but
it.
I see over here you are comparing the results as well, right? Yes, comparing XC and XT. So that means the tool has been
Yes.
executed, right?
Yeah, in this case, we're looking at the result. Like I said, we're just caching the tools. We didn't say, we don't want to have randomness just because Google today is not responsive or just because, I don't know, Selenium just doesn't work right now or whatever. So I'm not saying that we're not evaluating with the tools. We are using the results of the tools. Just we're assuming that there's a cached version of it already instead of invoking it and wasting
Okay, so
time and wasting.
you're using a fake tool in some sense. Like you're using
Exactly, it's like a mock-up.
I see
Yes,
it. So it's not that you're not executing the tool, you are mocking the tool execution.
yes,
Ah,
exactly.
okay, that makes more sense. So you're actually still evaluating what comes out after the tool.
Yes, of course.
Oh, okay,
Because
then the evaluation makes a bit more sense here because then we will be able to see what the tool output is.
yeah, of course. Like it would get a result. It sees the output of the tool. It just works with an idealized or cached version of that tool. Because otherwise, like I said, if Selenium didn't work right now, or if right now Google is unresponsive, or I don't know, whatever happens, that would be a really bad situation for a benchmark, right? To just be dependent on this random tool right now, what it does. And that's why when I said we're not accounting for the tool in our score because we're not evaluating the tool, we're just mocking it in the end and say that
Nice.
it would
Yeah.
call it, but this is the cached representation of it.
So there's another thing I have to ask is that when the plan is generated, if let's say after one step is done, do you refine the plan or is it always the same plan from the
No,
beginning?
no, it gets updated. So the idea, I mean, in this case, this is a general evaluation protocol. This vertex protocol is general for any even non-linear, so non-sequential task scheduling and everything. So you could have
Nice,
basically
nice.
a highly non-linear scheduling and so on. But the big but in the implementation, if you look at the code, you will see that we focused primarily now on sequential scheduling of tasks, meaning that one after another just gets processed. Because believe me, even in sequential task scheduling, it breaks and the LLM doesn't know what to contextualize and so on. So we don't have to even account for starting with non-sequential, like, oh,
Yeah.
I have to do this before I have to do that. And now let's go back and whatever, and forget
I
it.
understand. Yeah. I've been doing this agentic framework. Now it's called TaskGen. Before that was called Straight JSON. So
Mhm.
I spent 2 weeks trying to refine the prompt just so that it can do the planning well. So,
Exactly.
so,
See,
so it's difficult. I mean, I got something that is working fairly well already. It was painful, the process, but I think it's worth
yes,
it. Yeah, so
yes,
I understand where this is coming from. LMs are not very smart planners. You
no,
need to prompt it very well
exactly.
with chain of thought, reflect a bit, come out with the list of
Yes,
steps and then check the steps also, not easy. So
yes,
yeah, I do understand why the eval, sometimes you want to have a perfect tool. I mean, even the plan itself, the plan
yes,
might be wrong, then the whole eval is gone. I mean, you'll get
exactly,
result.
exactly.
Yeah, so there's a lot
Exactly.
of mm,
That's exactly the point. And that's why we like this is how we scored. Where is it? That's why we how we scored them in the end, right? You see here clearly, like we account for that error that it did, right? We account for it. We just move on and just pretend it was okay, and then let's move on and just do the next thing and do the next thing. But obviously, if this would work, the entire computational graph, then it obviously would be somewhere at least somewhere at 0.87 or whatever around here. But all of them are almost unusable. Obviously, GPT-4 and so on is much more proficient because it understands at least sometimes the classification and selection of the right tool, or is doing some extraction in a way properly. But the rest is like really not usable at all.
understand. This is another question I have on the benchmark is that prompt engineering plays a huge role here in the results.
Mhm.
How do you decide which prompt to use in order to like prompt the
So
next
that
one?
that's also, as we address in the limitation section a bit, like we started off with this project, I mean, over a year ago, right? So we started with GPT-3 back then, so there might be some inherent bias towards towards GPT family of models, if you want so, right? And we obviously refined over the last year and so on many of the prompts, but sure, there could be that there is much better versions of it and so on, but at some point you have to compromise. So yeah, and what assures me a bit is at least that you see that Gemini Pro and so on still works with these prompts
I see. So the prompts
respectively.
are heavily configured for GPT series and then
Yeah.
used for other models as well.
Yes, exactly. So we're not now prompt engineering for each of individual model, because in the end, that's kind of like not the idea to move forward, right? It's not like because if this would be aspirable to do, then it would mean that with every new model version and every new update, you always would have to fix your prompts to have the nice performance for this model, and now the next version
Uh,
comes out. Now for this
uh,
model, we have to that would be really really wrong in a way. So we're
or what
saying
you
like,
could do
look.
is you could have the benchmark fix. And then if people want to do a prompt engineering challenge, they can prompt engineer and see how high they can hit the benchmark.
Yeah, all of them. Yeah,
Yeah,
that's a cool idea. That's a really cool idea, because that's what you
because
could do now and
because
see
I
how.
mean the outcome is fixed. It's just like, can you get the model to perform better using the prompt? Then because right
Sure,
now you're using a fixed set of prompts that might
sure.
and that fixed set of prompts is actually inherent in the symbolic AI framework, right?
Yes.
How to do
So
the function extraction and stuff. So actually, if I were to collaborate with you and then like maybe we could refine the prompt a bit, the scores might be even better.
yeah, all of them.
Right?
Yeah, exactly. But for all, not just for one of the models, right? It should be like collectively increase, right? The because that's the idea, right? You have better prompts to collectively increase all scores of all models. But I fully agree that that would be something really interesting, because then you would see maybe even some patterns, as that step by step, or these kind of ways of prompting and them sometimes help. But yeah, uh, most things that we saw is often, or most issues that we saw are to, some these models, for instance, all of these open source models specifically, to better follow instructions when you to tune them in the future, to better follow instructions, to basically just output the format you want, because we often use for instance, Markdown format, because we saw that this is actually really good for Gemini, GPT, and all these models work very well. And when you ask it, like, produce a code, but please, everything should be always in this ticked format and Python and
Yeah,
whatever. And sometimes it works, like Mistral also gets it sometimes and so on. But most of the time is done again, like it just, the more, especially the more complex the prompts get, the less proficient they get to understand
I think the open source models, you need to break the prompt up into separate steps, smaller modular steps, then it's better understandable by the model. Too
Sure.
complicated, it's hard.
Yeah, but then it's like, then it kind of again defeats the purpose, because then it's like every step becomes handcrafted and modeled and so on, and
Understand. Yeah. I'm agreeable with the way you tested it because I think there's no real good way to test all diverse models differently, because if you prompt engineer for each of them,
yeah,
then it becomes a prompt engineering challenge rather than a benchmark.
exactly. So that's very good.
But actually, I
Thank you.
do have about like 10 minutes left. Maybe we want to
Yes.
go dive straight into. Are we done with the paper already? Yeah, I was thinking we could.
Yeah, so in general, we're done. There's just some more details if you want to look at, but yeah, we can basically skip that and just look into the code. So if you look at the benchmark directly, um, you might see, I mean, there is the main tests, obviously, which you can trigger, and some you can read me
So
what
we
it
don't have to
does.
implement the M and D algorithm, right? It's already inside here, right?
Yeah, everything is already inside. You don't have to
Yeah, because
implement. Like,
for people who want to want to use this benchmark, the equation can be quite scary. So
yeah,
the equations are all implemented. You just need to run this test dot py, right?
yeah.
And
Like,
it'll be done.
the exactly, the more challenging thing is probably to because we have also this package managing and all that stuff. So basically everything should be installed. Like when you use symbolic AI, like embeddings models, the llama cpp, the only thing that you have to look in is in the llama cpp, because you need to compile also the models for your architecture. So there's like some additional steps that you might look into that. And then you might also have to set up the config, basically, where you have the API keys for these models that use API keys, and for the other ones, it's basically just setting the port. Actually,
So you
that's
need
the only
to
thing.
actually host your own local llama model in order to run the llama.
Exactly,
But if you
exactly.
don't have a llama model, you can just skip that, right? You can just
yeah, exactly. You can select also which models you want to use. So this would be like the full test. If you like do this test pi, and then you basically have the association context, program synthesis, multimodality bindings, yada yada. But you can look then also if you want just a subset or whatever of these models. You can look, and there's basically dash dash models, and you give it just a list of models you care about. So you can basically put that in there.
nice.
Then basically there is all the source code. The main thing is actually the function.py here. So it follows the same structure as all other packages from our previous package managers. You have this package, it does JSON, where you have a version number and so on, some small description, and the main entry point if you want. So the evaluate benchmark entry point in source func, which is basically source func. So you could basically even call the benchmark from other projects directly from importing the expression. And then you basically just do, here it is. I mean, it's a bit of big one, but yeah, this is basically the expression, the evaluate benchmark expression. Has a prepare statement in this case where all the models get initialized and so on. So it basically initialize some global objects here first of all. So this global symbol primitives basically just means we're registering some methods to all the symbols. So we have some cool macros, if you want, so in the framework, where you can globally add a mean embedding property or some cross-validation properties and so on. There's just technical details right now, but this measure function, for instance,
So
we have a measure.
practically, if you want to run the benchmark, do I need to care about all this?
So
Not
no,
yeah.
no.
It's
I'm
just
just
a
explaining.
yeah.
I'm just explaining because also you see here how we, for instance, register the embedding model at runtime. So basically, in one line of code, you actually don't even have to manually install the packages outside. You could just run the benchmark, and at least this line would automatically register the embeddings model to the other engines in the engine
So
code.
for most people who want to just run the benchmark, you just take the
Yeah,
test.py, fill in your configuration details with the API key, run the test.py and everything.
exactly.
So this is
So
just the inner workings, right? Of
yeah,
okay.
and there are many other details here, but the main loop you might look at would be basically in the forward, where each experiment gets invoked with the different, properties that we just saw outside that you have as a configuration. And when you run this evaluation experiment loop, which is the main loop here, you basically just each experiment takes one of these functions here, one of these class files here. Sorry. So you have the eval computational graph, for instance, which would be somewhere eval in context, eval computational graph here, for instance. It gets somehow magically mapped. Don't care about how it gets mapped, but basically every test within this file gets now basically mapped here and gets mapped here, and you run over these different tests. So if you would look, for instance, in this computational graph file, you just need one specific, if you want to extend the framework, for instance, where is it? You just need to set with this naming convention test underscore workflow, for instance. So everything that starts with test underscore gets automatically mapped to the global
And
tests.
let
Then
me guess, it's because of the toggle test decorator that
no,
does.
this is a mock-up decorator. So this is basically, you could also mock the results when we did experiment. Like, imagine you're developing different new tests, for instance. You don't want, when you just run it, the benchmark, you don't want to have to like wait for the other test to finish to get to your new test. So you basically could just say active, set false globally somewhere here.
Oh, so the mapping of the test is actually done
Just
in.
by name convention, yes. So if you have
Oh, you
uh,
basically do you just get all the functions in that
exactly,
and then you just
which start with test underscore.
check for name
Yes,
whether it starts with test underscore, and then that will be added to a list, and then you submit,
exactly. And then
right?
everything gets evaluated. Yes.
Where is that done though? Where's that logic done? Is
For
it
what?
done of mapping everything? Is that done in the
Ah,
function of
yeah,
UI?
it's in the function somewhere here in the function. I don't know.
Understand.
Load test functions here.
So the reason why you did this, let me guess, is because you don't want to put everything in a list by default because it can be hard to represent the tests.
Yeah, also you want to have different files, and every file should have maybe some, you want to easily extend this, and you might, want to have in the future maybe more evals and so on.
Okay. So
And
I mean, if you want to extend this, if you can just name it like test 1, test 2, test 3, test 4,
sure.
like
Yeah,
as
sure.
long as the name doesn't clash with the
Exactly.
existing names. Mm.
Because otherwise it gets overwritten. Exactly.
All right, cool. Let's go into each of the benchmarks, and then maybe you could explain what you are testing here. Like give an
Yes.
example, input and example output, and then you just explain why you did this test, like the
Mhm.
rationale for what you are, or and like what you are focusing on to evaluate.
Yeah. So maybe let's, yeah. And what is also, by the way, I also have to mention this once. The aggregate you see here, this is basically an object that you get passed on from outside. So this is kind of like the interface, test underscore, and then you need an aggregate, which is basically an object that you can aggregate the results towards. This is uh, some new expression in our framework where you can easily use the pipe operator with the aggregate, and then you can just write any name you want. So this is a dynamic type to object. You could just say this is my name, and then it automatically creates this new object if it doesn't exist, and it pipes and adds the results without changing anything from the left hand side. So basically, whatever you do in the left hand side, you could do embeddings, you could do whatever you do, or get a score out of it. And when you pipe it with this object and just name some subspace, some like a naming convention or whatever you want, then it just copies the result into it and returns back the original object.
Do you need to write this in? If you create your own test, you also need to write the pipes as well as a site.
You don't have to write anything. It just so you don't have to use it if you don't want to, but then you don't have access to maybe embeddings that you want to analyze. You don't have access to, like, this is kind of like a
It's basically a hack for doing some tinkering, right? So if you don't need to do the tinkering, you don't need this.
yeah, yeah. It just needed as an interface. Maybe it just needed as some object comes in, and the other part of the interface is you have to return a succession, like true if you ended up until the end, and a score, final score. So yeah, that's basically what you kind of need to return. Yeah, so that's the whole interface basically. If you're interested in the details, again, you can look at here this part of the in the func.py. You see here run with backoff, basically is here using calling each test function from the list. As you said before, you have a list of objects which basically passes on the aggregator, maybe some quarks, which in this case are not existent, and just returns the result and the info object. So this is kind of like what you just saw here for every test, the same protocol.
Okay.
Okay. Yeah. So let's look maybe some examples. Let's start with some simple examples. Maybe here in context associations. I mean, the most simple thing you could do is obviously just if you have just a true false statement, so it's like a Boolean succession. Yeah, but this is just if these are simple association problems, but more complex ones are followed down here. If you, for instance, try to clean up a text, for instance, with all this randomness in between, then you obviously care about you basically have your base result that you would have expected, your symbol that you kind of have with this uncleaned tokens and so on in between, or these characters in between. And then you basically use the operator clean, for instance. In this case, it's a function from our framework. And what you get as a result, basically, you look at some randomness, as I told you before. So randomness in this case is just basically a list of different random different random where is it? Sequences. So as you see here, random sequence
All right.
in different variations and so on. And can you go back? Yeah, okay. And then basically you just compute here in a a mean vector in this case, because we just want to see what is the kind of like mean distribution of randomness. And then basically you use the measure function to measure against the base. So base is in this case hello world. This is your random
This is
vector.
the random string. This is the Z
Exactly.
talking about in the equation.
Exactly, the z rand, for
Yeah.
instance, we saw there, and then you
Yeah.
basically normalize. In this case, scaling is 1 0, because there is no you just expect exactly this result. There is no smaller case, uppercase, all, and so on variations, because otherwise you would have to account for that also, that you even among solution candidates there would be some variation. In this case, there is no variation among solution candidates, so it's just one. And then basically you just say, okay, now base comparison, how far is like the result that we got from the cleaning operation measured towards the base, and with the renormalization here. And that's kind of it. So that's how we then basically get the score, and we can just get the value out of it and return.
Okay, so this in-context association looks like it's testing out the inbuilt symbolic AI functions like test filter, test the filter operation, test the clean. I mean, there are other stuff like query and stuff.
Of course,
So this
exactly.
in-context is basically whether it can fulfill the symbol class functions well. Is that correct?
If it can use one of the many of the associations and class functions that we have built in, because like one is the cleaning operation, but there are also like filtering operations where you have you want to filter out like physics, sports, whatever, and you just want to look at the science subjects, which is just a full text filter. And this is exactly as you said with the, like in this case, you would have expected the GPT model or any LLM model now understands the subject, understands the list of subjects, and then starts to filtering all the results out properly. And then you could just test for succession. But there is also like, association things like equality, or like adding to
I understand. Yeah. Also, if people extend on to your benchmark, is it all right if they don't do anything related to symbolic AI based functions?
Of
Because
course. No, that works for sure, because right now this is for us, like, think of it this way. This is like for us, we can use our own set of functions that we already defined, right? That's why we kind of showed it also this way, because we have the plus operator overloaded. We have the, I don't know, obviously you can write your own function if you want to. Let's say, what do you do with two symbols, and then you come up with your own operator. That's the whole flexibility and idea of symbolic AI, that you could symbol, for instance, can get a new operator attached to itself. Actually, that's why I tried to explain this earlier with the func.py and with the measure. This is not in symbolic AI a default function. The measure does not exist in symbolic AI, actually. Measure is actually a utility function created specifically for the benchmark, where you see here, this is the function measure, where it gets self, which is the current symbol object, other, which is the other object you're measuring against. And then basically the normalize, as you saw it before. And then there is here these, what do you do with it? And in this case, we compute the distance with the kernel, with the respective kernel. So the distance is basically somewhere here, right? So this is kind of what, and now this is what you just saw before, where you asked me, do we need to do this? And I said, like, well, no, you don't have to do anything about this. Like, this global symbols primitive. But if you want to, let's say, create a global method that is just specifically for your use case or for whatever you want to develop right now, you can just attach that to any symbol, and then it's globally available for everyone. So in this case, this is what we did with this kind of operation here, where we said we are attaching the measure function to the symbols, and now you can just measure the different distance between two different symbols over the binding of embedding vectors. So this is kind of what happens in the background.
Sounds good. Okay, so actually in the last 5 minutes, because I kind of got to go soon. Do you want to share another eval, or like do you like to just conclude already? Like
I think we can conclude. I mean, there is like if you want to really look at a full workflow, I encourage you to look at the computational graphs, because this is probably the most proficient thing. And you will see here, for instance, how we created an entire computational graph in a very structured and nice way. Like you see here, paper with method, related work, and so on. Like, this is our expression language that we use in the background. and how we structure the creation of the graph. And this is basically like PyTorch. Think about like in PyTorch or
Yeah,
whatever.
or like Keras, you do a sequential, that kind of stuff.
Exactly. So you just stitch them together, and then you have an expression. The expression
Oh,
you then
wait, this
run.
expression paper is created especially for this, is it? Or is it already inbuilt in Symbolic AI?
No, this was created specifically here for the benchmark because we wanted to evaluate like a full generative process of a paper generation process, but there is also another process in here you could look at. And then you can just say like, you actually even have the full access to the entire computational graph, because oftentimes when you stitch things together like this, you actually get intermediate results in the generative process, in each of these steps. But you actually, at the end, if you just run it, you would just get one result, or one output, right? What's the last output? And that's kind of bothersome. So what we also built in is a new linker object and so on. So when this is available in the default symbolic AI package, you can use the linker, for instance, and like query it, like find, and then you basically name it what you're looking for, and then it retrieves the object back and so on. And then you basically could look at the intermediate results of the generative process, and do the measurements also on top of them. So that's exactly what we do then when we are evaluating how good did the method generation happen, how good did the related work, or maybe intermediate things work, and so on. So and this is how we score all of it, and then we have a final score at the bottom that we integrate basically, or in this case mean. But yeah, that's kind of like the most proficient way if you want to look at this kind of thing, or some other examples here. But yeah, let's maybe conclude it, because I think there were many details. This is basically what you get, by the way. If you're curious, how does the entire computational graph look like? You can also visualize it, and you have some parallel executions of some stuff, so some sequential stuff around here. Here's the title generation, for instance. Here's the abstract, and so on. So
So
this
we're
is
talking
kind
about the
of
sequential graph for what you just shown just now for the eval.
exactly. This is the computational graph of what you just saw with this thing here.
Oh, nice. So is the LM expected to create the whole graph out?
So not the LLM, but we have an expression in here that can visualize the graph if you want.
Oh no, but what is okay? So can you explain to me what is the input to the LM for this, and what's the output?
So in this case, the LLM always gets as an input, if you want, so is the sources or the citations, for instance, and the output is obviously with the respective site or source or whatever of or one of these expressions, where it has to produce content related to this source. And then we're evaluating the quality of the content it produced. So is the citation really citing, talking about what we expected it to talk about, or is it just going off randomly or so? So this is, for instance, for this computational graph test, what we're looking here. But the other one that you saw in the paper with the planning and so on, the sequential planner thing here, this one, this is basically further down. So if you go further down here, you will, further up. So here's the solutions, tools. Well, this is way too much. That's why I didn't want to go over that, because there's a lot of here test workflow. So if you're curious how we do and planning and executing planning in a sequential way with different tools and all that stuff together, this is the test workflow, this is full out generating even the plan. Whereas in the example that I just showed you with the paper, in the paper example here below, here the plan, if you want, so is
The
the
plan is
expression like
given in some sense.
exactly
You just
exactly. So
you're just testing its execution.
exactly. So this would be like the full, and this is probably not probably, but this is exactly why you also see some quality in here, because obviously GPT-4 and other models also are like good at generating stuff. But when you really just want to have the plan and everything else generated and run, then obviously
So the planning is not good, right? For this.
exactly, that's not good. So
How do I
that's
set my own custom goal here? Okay, so what your framework here is actually very relevant to the task gen framework I'm creating, because I'm creating an agent that plans given a few functions and capabilities. It is a function-based planning. Like how do I set up the goal here? Like the goal, do I write some? Okay, so this is the thing. So actually, I just need to modify. Can you scrub a bit? Scrub.
sorry.
You want to see where this is.
Up. Okay, there's a solution already. So it's
So-
basically everything is in JSON format, as you see here.
So where's the input to this? The input is, or it's part of the solution, right? Task one, search for this. So this will be the goal. And then
exactly. This would be a
what
goal. This is another
expected
goal.
interface is what function do I expect it to call? Expected result is what's the
Yes, exactly.
result. So the
Exactly.
simple Google results is the mock-up of the Google search.
Yes, exactly. You see, this is exactly as we discussed earlier.
Okay. Then the expected next task will be the next step of the plan. And so you keep going through this. And how is this
Yes.
ground truth generated?
Well, this is just defined. So you would say like, we had like some tools included here because we have some, obviously, where is it? Further up. We have, let's say, you see here, for instance, like the plan generation template. We give it an example how to generate the plan, for instance, how we expect the format to look like, how we expect like what to do. And there is also a template for the tools that it has in the set of all tools, where I don't find the prompt right now, where it says like, for this capability, you can use the large language model. For this, here, found it now. For Google search, to be used, search facts of information and so on,
Nice.
and in the respective tool. And for browser, use basically open pages. But the point is like, to be used to extract information. And now this is also oftentimes where the LLM itself uses the LLM wrong, because oftentimes it uses the LLM to even get facts back, which we don't want. We want to
So
use it.
I can tell you what I did for the framework. For LM part, I just put use when no other function can be used.
Mhm.
Yeah, so
Yeah,
it
of course,
prioritizes doing the other functions first.
exactly. But this is exactly, and now you have to think about all the traits and hacks, and
Yeah.
and that's kind of why we say like we care more about semantic understanding than just hacking a prompt to until it works, because that's what we're kind of aspiring with this benchmark towards in the future. Also, this benchmark, I mean, the score that we have here, this is exactly the goal of the score. Maybe we can conclude it here. That you can now use this as a reward signal. That's also what we talk about in future work, as a reward signal for a reinforcement learning agent and so on. So basically, our idea is that, I don't know where we put this future work here, that we now can use this for credit assignment if you want, so in reinforcement learning, because now you have at each generative step basically a kind of a scoring how far off you are from from what you would have expected. And obviously it just has to have a monotonically increasing function if you want, so increasing score. The closer you are to the ground truth, the closer you are to the reference
Why
data.
not, rather than just a numerical score, why not give some constructive feedback that maybe can be used to modify the architecture?
Because you need this for in RL, you need a reward.
Yeah, correct. So I'm
Reward
actually saying that maybe we don't need RL. We can just, use the LM to
Yeah, but then it's difficult, because I mean, the whole point of our framework, when we said like we have this MP net, now the gradients, how do you propagate the gradients back into the computational graph? That's kind of the hard part, right? Because we're symbolic, sub-symbolic, we're jumping around between those two realms. And if you use an indirect method to get the embeddings, the question is now, how do you propagate or create gradients back that you can propagate and update the model that you used for generating the content. And whereas having a score, in this case, indirectly, you already just can use RL, right? For like any embedding model can be used now, and then you basically have an indirect way of using that reward signal to score
understand.
or to guide the generative process of the generator.
I'm,
So
I'm
that's
quite
kind of,
I'm, I'm quite happy that you're thinking of a long-term self-learning plan, because I like self-learning agents. This is heading towards there.
yeah.
But increasingly, based on my research in RL, I come to think that RL is very slow, and maybe a more informative signal might be better rather than just scalar rewards. So that's just my opinion. But
Could
I,
be.
I
I mean,
yeah, I think
but
RL
it's
is
also
fine.
nice. On the other hand, it's also nice because it has uh, finding a right number is hard, right? I mean, giving feedback, and like I said, also the gradients computation is hard. But in this case, you would have some number that abstracts the closeness, right? Which is actually a good thing, what we care about. So in this case, even if it's slow, RL doesn't have to be applied in every step, right? I mean, the idea is that's the cool part about foundation models. You have a foundation model. If you just care about few shot capability in general terms, well, you have already the model there, right? You don't have to even do anything else. You just few shot and you prompt it. But in the future, if you say like, but for this specific task, maybe it's more sensible to use a smaller model, but tuned, right? So it basically you've for one of these tasks, like classifying context or whatever, or for doing some specific traits, you might just use a more specialized model, and you just bind it to a functionality as we bind right now tools. You could just bind it for in context classification and just say like, use this small fast model to detect which context it is. And then it's enough to have a sparse reward signal, just saying like, oh, you're this far off or this close to it, right? And yeah, you would just tune this one thing. But yeah, this is
Anyway,
kind of
I'm open to multiple views. I'm just giving my view here. So I do like whatever that you have created so far. Like I think it's very ambitious the way that you align different symbols. Maybe it's a good time to conclude here. Like the main thing is what we see right now is just only the beginning, and like a lot of things can be done. So even the
yes,
benchmark that you have created to evaluate is just the beginning. I
yes.
think it will evolve. That's why I'm giving like some feedback here. Like I think it could be a bit
Oh,
more.
it's good. It's very good feedback. Thank you.
Yeah. So I do think the idea of like not having only one ground truth, but using similar answers for ground truth, that is a great idea. Whether or not this MND distance is the best thing, I don't know. Yeah. So I mean, there's really no good way to evaluate unless you give MCQ, which obviously is not very realistic. Yeah. So MCQ is what people use for MMLU, but that's
Yes.
not. Yeah. So that I think there's a lot more to be done for like large language model research and how to evaluate things well. But one thing for sure is like based on the symbolic AI, I think one of the key few things you found out is that like LLMs are not very good planners. They
Yeah.
yeah. Yeah. So that needs to be improved. Maybe as a last few words, we'd like to share more about like what you have learned from building symbolic AI and what your future plans.
What I learned. I mean, I learned a lot along the way, right? I mean, there are so many details that I had to dig into, and especially like come out of the comfort zone because I'm originally coming from reinforcement learning, domain adaptation, so I had to like really dive into logic and other things and so on. So that was a lot to take in also and to analyze and see how we can, because you can't build a framework about symbols if you don't understand what symbols are and all that stuff around it, right? So yeah, that was many things I learned. There were too numerous to count them. Maybe the more significant part where we're going towards right now in the future is, like I said, there is ideas in obviously using directly our score for fine tuning RL agents and so on, because we want to have autonomous agents. But also we're looking into ideas how we can further fuse together with PyTorch from the graph structure and find ways to do proxy gradient computation. So that's kind of one of the things, as we talked right now. You have this embedding model on the side, kind of gives you already some, in a way, symbol vector valued representation. Is there a way to compute the gradients over a symbol basically back to its input or so, with a proxy in between, right? So that would be kind of the idea, and that it still optimizes something sensical, like, because I know there are also papers that showed how you can drop out, for instance, in a transformer during training, you can drop out different modules, right? Randomly just dropping out entire blocks, transformer blocks and so on, and it still optimizes towards a global objective, right? The same inspiration comes here, and they would say like, is there a way to have multiple symbolic representations in between, where you at the end have an objective, but then you kind of propagate over proxies back to your even your first stage. So that's kind of one of the things that we're looking into. And yeah, and many other things of autonomous agents, and now optimizing what we just learned from, and just built the groundwork for the next steps. Yeah,
Nice. Thanks so much for sharing with us all this. I mean, I look forward to you expanding this project, and I'll share with you some of the lessons I learned also in the agentic framework. I think maybe that
please,
can help improve the planning abilities in symbolic AI as well. Yeah. So
please,
yeah.
everything.
I spent 2 weeks configuring the prompt. It was a headache. I tell you. Yep.
That is
But
for sure very
this shows
valid one.
how fallible language models are, like how fragile in some sense, because it's very heavily related to the training set and how you prompt the model to get the capabilities out from that training set. So if the training set changes, like OpenAI releases a new model, you kind of need to reprompt some of the stuff again. So that's the challenge and opportunities for LLM. They are versatile, but they are also quite susceptible to change. And yeah, using
Yes.
frameworks like SymbolicAI, can help you to like do fewer of the prompt stuff. You can just straight away use it for execution. So yeah, just a shout out again. Do check out their repos. Is the you want to give the GitHub link here? I'll put the video. So yeah, it's the SymbolicAI. You can try it out. A lot of hard work has been put in to engineer the prompt so that it works. So, but there's a caveat, works only with GPT because from the eval, you can see that open source models don't work too well. So yeah, use GPT for now. Yeah.
Yes. Or Gemini. I mean, Gemini works nicely in many ways. So it's really good as a runner-up, I would say.
And yeah, thanks so much. And yeah, we'll be having Marius back again to share more once he's
Thank you.
actually actively developing products with his framework. And it'll be interesting to see what the framework can do. So stay tuned
Yes.
for that. All
Thank
right.
you very much.
Okay. Bye,
Thank you,
Ren.
John.
Bye,
Bye.
Marius.
Cool.